Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're going to continue our lecture on isomers, and our first topic of interest is configurational isomers. Configurational isomers are distinct from conformational isomers because they cannot interconvert without breaking and reforming covalent bonds. Now, this category includes two important types: enantiomers and diastereomers, both of which we'll cover in this lecture. But to understand configurational isomers, we first need to talk about chirality. An object is considered chiral if its mirror image cannot be superimposed on the original object. A simple way to think about this is to consider your hands. They are mirror images of each other, but no matter how you rotate them, you cannot superimpose one hand onto the other. If you place your right hand on top of your left hand, this is the easiest way to see an example of this. And molecules, they work in the same way. For a molecule to be chiral, it must lack an internal plane of symmetry. Now, identifying and distinguishing stereoisomers, that involves a systematic approach. And there are three key topics we're going to cover to make this easier. First, we're going to learn how to identify chiral centers in a molecule. Second, we're going to learn how to assign the configuration of a chiral center as R or S based on the Kahn-Ingold prelog priority rules. Finally, we're going to learn how to apply these assignments to categorize stereoisomers as enantiomers, diastereomers, or meso compounds. Let's begin with step 1 and learn how to identify chiral centers. A chiral center is a carbon atom that is bonded to 4 different groups. Identifying the number of chiral centers in a molecule is important because it determines the types and number of stereoisomers possible. Your first step whenever you're analyzing any molecule should always be to locate all of the chiral centers. This means examining each carbon atom and checking whether it has 4 unique groups attached. That's the definition of a chiral center. If a carbon atom meets this criteria, it is considered a chiral center. To better understand how the number of chiral centers relates to stereoisomers, let's take a look at this table here. If a molecule has 0 chiral centers, then it is achiral, meaning it lacks chirality and it does not have stereoisomers based on chiral centers. If a molecule has 1 chiral center, it can form enantiomers, which are non-superimposable mirror images. With 2 chiral centers, the molecule can form both enantiomers and diastereomers, which are stereoisomers that are not mirror images of each other. A useful rule to remember is this: when a molecule has X chiral centers, it can form up to 2 to the power X stereoisomers. However, there are exceptions, and we're going to cover those exceptions a little bit later. Let's take this information and let's apply it to an example problem. This example problem says, how many chiral centers are present in this molecule? To answer this, we're going to start by examining each carbon atom and its attached groups. If we look at this carbon right here at the end, this carbon is a methyl group, so that means it's attached to 3 hydrogens that are not explicitly drawn in bond line. Remember, a chiral center is one where the carbon is bonded to 4 different groups. If there are 3 hydrogens, that's not 4 different groups. So this carbon at the end is not a chiral center. What about this next carbon right here? This carbon is attached to 2 hydrogens. So it's not possible for this carbon to have 4 different groups if 2 of them are hydrogens. Therefore, this carbon is also not a chiral center. What about the third carbon here? This carbon is bonded to an alcohol group. There's also a hydrogen here. then this ethyl group, and then this 3-carbon chain with a bromine. Those are 4 different groups that carbon is bonded to. So that means this carbon is in fact a chiral center. What about the next carbon? This carbon is bonded to a bromine group. There's also a hydrogen, an ethyl group, and then this chain with an alcohol group. Those are 4 different groups that the carbon is bonded to. So this is also a chiral center. Let's look at our next carbon. This carbon has 2 hydrogens, so it cannot be a chiral center. And this end carbon is another methyl group, which also cannot be a chiral center. So this molecule has a total of 2 chiral centers. Now we can move into step 2. Here we're going to learn how to assign a chiral center an R or S configuration. Assigning R or S configurations involves a systematic process, which we're going to break down into 5 clear steps. Step 1 tells us to identify the 4 atoms or groups that are directly attached to the chiral center. These groups are going to be prioritized based on their atomic properties. Step 2 tells us that we're going to assign a priority to each group based on the atomic number of the atom that's directly bonded to the chiral center. The atom with the highest atomic number receives a priority of 1, and the atom with the lowest atomic number, usually a hydrogen, it gets priority 4. Then step 3 tells us if 2 atoms are the same, then you want to move outward 1 bond at a time until a difference is found. For example, a group with a carbon that's bonded to an oxygen, that will outrank a group with a carbon bonded to a hydrogen. Also note that double bonds count as if the atom is bonded twice to the same element. This might be a little confusing at first, but it'll make more sense as we tackle some problems. Step 4 says, ensure the molecule is oriented so that the group with the lowest priority, priority 4, is pointing away from you on a dashed wedge. Again, this means that the lowest priority group, priority 4, it should be pointing away from you. It should be going behind the plane of the page. If the 4th group is already on a dash, wonderful, you can move directly into the next step. If not, don't worry, we're going to address what to do in a moment. Then our final step is to trace a path from priority 1 to priority 2 to priority 3. And if the path moves in a clockwise direction, then the configuration is R. And if the path moves in a counterclockwise direction, then the configuration is S. Now let's go back to step 4. This is going to be really important for us. We need to learn how we deal with a scenario where our 4th priority group is not on a dash. We're going to use a trick so that we're not wasting too much time on the MCAT trying to rotate things in our head. So here are our 3 scenarios and what we can do to handle that fact and assign the correct R or S configuration. We already stated earlier that if the 4th group, the 4th priority group is already on a dash, then you can simply follow the sequence 1, 2, 3 and assign R or S accordingly. But if the 4th group is not on a dash, what do we do? There's 2 possible scenarios from here. The 4th group can be near the dash. In that case, what you want to do is determine the 1, 2, 3 direction and then assign the opposite configuration. So if 1 to 2 to 3 is counterclockwise, usually that would mean the S configuration. But that's only if the 4th group is on a dash. If the 4th group is near a dash, you have to go ahead and assign the opposite configuration. So S's become R's and R's becomes S. The other scenario is that your fourth group can be across a dash, opposite the dash. In this case, you can go ahead and determine the 1 to 2 to 3 direction and assign it R or S without any changes. So let me reiterate. There are 3 scenarios here. Your fourth group can already be on a dash. If your fourth group is already on a dash, you can ignore it. You can figure out your direction going from 1 to 2 to 3. And whether it is clockwise or counterclockwise, you can go ahead and assign it as R or S respectively. The other scenario is when your fourth group is near a dash but not on it. In this case, you can go ahead and ignore the fourth group, figure out your direction from 1 to 2 to 3, and then give it the opposite assignment. And then the final scenario is when your fourth group is across the dash. All right, it's opposite the dash. In this case, go ahead and ignore the fourth group, figure out your 1 to 2 to 3 direction, and just assign it R or S based off of that direction without any changes. So let's apply this to an example. Earlier, we said this molecule has 2 chiral centers, one over here and one over here. Let's go ahead and assign each chiral center. Let's start with assigning this carbon right here. This carbon is bonded to a bromine group that's on a wedge, a hydrogen group that's on a dash, and then a carbon group on the right and the left. Just looking at this, it's easy to assign priority 1 and priority 2. The atom with the highest atomic number gets priority 1, which is going to be the bromine group. And the atom with the lowest atomic number, that's going to get priority 4, and that's going to be the hydrogen. But what about priority 2 and 3? This chiral carbon, it's bonded directly to 2 other carbons. How do we distinguish which carbon gets priority 2 and which carbon gets priority 3? Well, this leads us into step 3. If 2 atoms are the same, move outward 1 bond at a time until a difference is found. This carbon on the right side, it's bonded to another carbon and 2 hydrogens. And the carbon on the left, it's bonded to an oxygen, another carbon, and a hydrogen. And from here, it becomes really easy to assign priority 2 and 3. And that's because oxygen has a higher atomic number than carbon. So the carbon on the left side gets priority 2, and the carbon on the right side gets priority 3. Now I'm going to redraw it so it becomes easier to figure out if it's a clockwise rotation or a counterclockwise rotation going from priority 1 to 2 to 3. So on the wedge, we have priority 1. On the dash, we have priority 4. Our carbon to the right is priority 3, and our carbon to the left is priority 2. Now, the fourth step is where it becomes important to recognize where our fourth group is. We want it to be pointing away from us on a dash, and it in fact is. When this is the case, we can ignore group 4 and then draw our arrow from priority 1 to 2 to 3. This is counterclockwise, which means it gets assigned an S configuration. So this chiral center is an S configuration. Let's do the other chiral center. So we're going to erase everything and start from step 1. That carbon is attached to an alcohol group, which is on the dash, to a hydrogen that's on a wedge, and then 2 other carbon groups. Looking at this, it's easy to determine which group gets priority 1 and which group gets priority 4. The atom with the highest atomic number gets priority 1, which is our oxygen. And the atom with the lowest atomic number gets priority 4. That's going to be our hydrogen. Now, what about priority 2 and 3? Well, we have a tie here, but they're both carbons. So step 3 tells us to move outward one bond at a time until a difference is found. The carbon on the right side, it's bonded to a bromine, to another carbon, and to a hydrogen. The carbon on the left side, it's bonded to another carbon and 2 hydrogens. Here it becomes clear which group gets priority 2 and 3. This carbon on the right gets priority 2 because it has bromine, which has a higher atomic number than carbon. So this carbon is 2 and this carbon is 3. We'll redraw. On the dash is priority 1. On the wedge is priority 4. Pointing to the right is priority 2, and pointing to the left is priority 3. Now, step 4, we need to pay attention. Where is group 4? Group 4 is on a wedge. It's right next to the dash, but it's not on it. So that means we have to use condition 2. If the fourth group is next to a dash, we want to figure out our 1, 2, 3 sequence and then assign for the opposite configuration. So we're going to ignore group 4. We're going to draw our arrow from 1 to 2 to 3. This is counterclockwise, so it would typically be given an S, but in our condition, we're going to give it an R since the fourth priority group is not on a dash, but next to it. So this chiral center is R. This one's S, and this one is R, and we have completed this practice problem. That means we can move into step 3, where we're going to understand the relationship between different stereoisomers. Let's start with discussing enantiomers. Enantiomers are non-superimposable mirror images of each other. This means that no matter how you rotate one molecule, it cannot be perfectly overlaid onto its mirror image. For a molecule to have enantiomers, it must have at least one chiral center and a lack in internal plane of symmetry. Now, enantiomers, they have the same physical and chemical properties in achiral environments. They're going to have the same boiling point, melting point, and solubility. However, they behave differently in 2 specific scenarios. The first scenario is in regards to how they rotate plane polarized light. Enantiomers are going to rotate plane polarized light in opposite directions, but by equal amounts. One enantiomer will rotate the light clockwise, while the other rotates it counterclockwise. And this rotation is quantified using the formula you see here. This formula tells us that the specific rotation is equal to the observed rotation in degrees divided by the concentration in grams per milliliter, and that's multiplied by the path length in decimeters. The second scenario is in chiral environments. In the presence of a chiral reagent or catalyst, enantiomers may react differently, and that makes this distinction very important in biological systems where molecules are inherently chiral. So, once again, enantiomers have the same physical and chemical properties in achiral environments, but they behave differently in 2 specific scenarios. The first one is in regards to how they rotate plane polarized light, and the other scenario is in chiral environments. With that, let's discuss diastereomers. Diastereomers are stereoisomers that are non-superimposable, and they're not mirror images of each other. To form diastereomers, a molecule must have at least 2 chiral centers. And unlike enantiomers, diastereomers have different physical and chemical properties, even in achiral environments. That makes them a little bit easier to separate and study in general. Finally, I also want to discuss meso compounds. This is a special class of molecules. They are achiral compounds that contain multiple chiral centers but have an internal plane of symmetry. This symmetry makes the molecule superimposable on its mirror image despite having chiral centers. For the MCAT, to identify a meso compound, you want to look for 3 criteria that are met. The first criteria is an even number of chiral centers, at least 2 chiral centers. Second, a plane of symmetry that divides the molecule into 2 identical halves. And the third criteria is opposite configurations, R and S, at every chiral center. Now, this seems like a lot of information, but what we're going to do to make it easier to understand is we're going to have a rubric for how to determine if a pair of molecules are enantiomers, diastereomers, or meso compounds. And then we're going to put it into effect with a practice problem. If we were comparing 2 molecules that only have 1 chiral center, there are 2 possible scenarios. If they have opposite R and S configuration, for example, this one would be R and this one would be S, then they would be identified as an enantiomer pair. If they were both the same, say let's say that they're both R and R, then they would be identified as identical molecules. What if the 2 molecules we're comparing have 2 chiral centers? In this case, there are 3 possible scenarios. If they have opposite RS configuration at every chiral center, then they would be identified as enantiomers. So if this one had R and R, and this second molecule we're comparing it to had S and S, notice that they have opposite R and S configuration at every chiral center. That would make this pair enantiomers. But what if they had some opposite and some same RS configuration? For example, what if this was R and R, and here it was S and R? That would mean they have one opposite configuration at this chiral center, and then the other chiral center, they would be the same. This pair would be classified as diastereomers. And then the final scenario is if they both have the same R or S configuration at every chiral center. For example, this could be RR and this one could be RR, then they would just be identified as identical. Now, there's one exception here that you have to be careful for. If there are 2 chiral centers and you had reflectional symmetry, and one molecule had R and S, and the other had S and R, then these 2 molecules are identified as meso compounds. This might be a little confusing, but let's put it into effect with this practice problem. This practice problem says, draw all of the possible stereoisomers and identify relationships between different pairs. So this is the molecule we're starting off with. Notice it has 2 chiral centers, which means it has 2 to the power 2 stereoisomers. It has a total of 4 stereoisomers. I have them drawn here, and they're numbered 1, 2, 3, and 4. 1 has both of these alcohol groups on wedges. 3 has both of these alcohol groups on dashes. 2 has the right alcohol on a wedge and the left alcohol on a dash. And 4 has the right alcohol on a dash and the left alcohol on a wedge. Now, there's also another important observation, and that is if we cut this molecule in half right here, this side looks like this side, which means it has a plane of symmetry that tells us that when we are identifying the relationship between different pairs of stereoisomers, we have to be cautious in identifying our meso compound. So let's begin to identify the different relationships between different pairs. We're going to start with comparing 1 and 2. The chiral center on the left is going to be noted as A, and the chiral center on the right side is going to be noted as B. When we're comparing 1 and 2, we're going to first compare chiral center A in both 1 and 2. In Stereoisomer 1, it's R, and stereoisomer 2, it's S. So they have opposite configurations at chiral center A. What about chiral center B? They have the same configuration. When you have one opposite and one same, this means you have a pair of diastereomers. So 1 and 2 are diastereomers. What about 3 and 4? Let's compare them. At chiral center A, they have S and R, so opposite. And at chiral center B, they have R and R, so same. So 3 and 4 are a pair of diastereomers as well. Now let's tackle 2 and 4. At chiral center A, one has S and the other has R. And at chiral center B, one has S and the other has R. So SS and RR, they are opposites at each chiral center. So that makes them enantiomers. Now we move on to comparing 1 and 3. At chiral center A, stereoisomer 1 has R and stereoisomer 2 has S. And then at chiral center B, stereoisomer 1 has S and stereoisomer 3 has R. Okay, this meets our criteria for meso compounds. First, there are 2 chiral centers. Second, there is reflectional symmetry. And third, one has RS and the other has SR. So they are not enantiomers, they are in fact meso compounds. Now we have 2 more we need to figure out. We need to compare 1 and 4, and then we need to compare 2 and 3. Let's start with 1 and 4. At chiral center A, 1 has R and 4 has R. And then at chiral center B, one has S and the other has R. So we have one same and one opposite. So these are a pair of diastereomers. Now let's move on to comparing 2 and 3. This is our final pair. At chiral center A, they both have S. And at chiral center B, one has S and one has R. So this is another pair of diastereomers. So we have identified the relationships between all of these pairings. With that, I hope this problem has clarified our rubric for identifying enantiomers, diastereomers, and meso compounds. Of course, we'll do more practice in our practice problem set for chapter 2. But we can now move into our last and final objective. Here, we're going to start discussing relative and absolute configurations and how they help describe the spatial arrangement of atoms or groups in stereoisomers. The configuration of a stereoisomer refers to how the atoms or groups are arranged in space. And this can be described in 2 ways. The first is the relative configuration. The relative configuration of a chiral molecule is its configuration in relation to another chiral molecule. We can use the relative configuration to determine whether molecules are enantiomers, diastereomers, or the same molecule. This is exactly what we just did in the last problem. The absolute configuration of a chiral molecule, that describes the exact spatial arrangement of its atoms or groups independent of any other molecule. This was what we learned when we went over the rules for assigning a chiral center an R or S configuration. So relative configurations when you're comparing the relationship between 2 molecules, and the absolute configuration is looking at one molecule, looking at each chiral center in that molecule and assigning it an R or S configuration. From here, we shift to E and Z nomenclature, which is used for compounds with polysubstituted double bonds. These labels are going to help describe the arrangement of substituents around a double bond in alkenes. So here's how it works. First, we want to identify the 2 substituents attached to each carbon of the double bond and assign priorities to them based on atomic number. This is similar to the priority rules for chiral centers. If the two highest priority substituents on each carbon are on the same side of the double bond, then the compound is given the Z designation. If the two highest priority substituents are on opposite sides of the double bond, then the compound is assigned the E designation. So let's apply this to the examples shown here. For this first compound, the highest priority groups on the double bond carbons are the chlorine group on this carbon and the ethyl group, on this carbon. Notice that they are both on the same side of the double bond, so it gets the Z designation. For this compound, however, the highest priority group on this carbon is the bromine, and on this carbon, it's this tert-butyl group. So they are on opposite sides of the double bond, meaning they get the E designation. To end this section and this chapter as well, the last thing we want to talk about is Fischer projections. A Fischer projection is a 2D representation of a 3D organic molecule, and it simplifies the visualization of complex molecules, particularly carbohydrates and amino acids, while still retaining important stereochemical information. For the MCAT, we need to know how to convert a Fischer projection into a bond line structure. And to do this, there's 4 main steps. The first step is to set up the backbone. The backbone is going to look like a table where the ends of the table are the groups on the top and bottom of the Fischer projection. Then from there, the middle portion is going to have the number of dots that align with the number of carbons in the backbone of the Fischer projection. So here our Fischer projection has 1, 2, 3 carbons. That means our table, the middle portion of our table is going to have 1, 2, 3 dots that correspond to the 3 carbons. So again, we started with our table framework. We put the top and bottom groups of our Fischer projection as the ends to that table. Then we drew 3 dots since we have 3 carbons in the backbone. And from there, we can move into step 2. Step 2 tells us to add the substituents. So for each carbon on the backbone, we want to observe the groups that are on the left and right sides of that carbon. Groups on the left side will be drawn as wedges, and groups on the right side are going to be drawn as dashes. So looking at our first carbon right here, we have a hydrogen to the left, so we're going to draw the hydrogen on a wedge. And then we have an alcohol group to the right, so we draw the alcohol group on a dash. And then we do the same thing for carbon 2. It has a hydrogen on the left side, so we draw it on a wedge. And an alcohol group on the right side, we draw it on a dash. And for carbon 3, we have a alcohol group on the left, so the alcohol group goes on the wedge, and a hydrogen on the right, it goes on a dash. And so we get the following structure. Now we move into step 3. Step 3 tells us to reorient to bond line. We want to convert this structure into a proper bond line diagram. So we ultimately want a zigzag configuration here. We want to change something in this table framework so that it matches the zigzag backbone that is standardized in the bond line convention. So the only thing we need to do here for this particular structure is change the orientation of carbon 2. We want to bring it downwards, so now we have this zigzag framework for bond line. When we do that, that means we are going to flip that group. When we bring it down, we flip it. So now the alcohol that's on a dash goes on a wedge, and the hydrogen that's on a wedge goes on a dash. And from there, our final step is to make sure that when we're drawing our bond line, we don't explicitly draw the hydrogens. And so we have gone from Fischer projection to bond line following these steps. And with that, we've actually completed chapter 2. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.